Good afternoon, everybody, and welcome. My name is Stefano Marcheris. I'm a professor here at KTH in computer science, and I'm also co-organizer here with Yuna, who at this point you know quite well, of this summer school on machine learning for space physics. So it's really my pleasure to welcome you first to Stockholm and to KTH. I really hope that this week is mixing knowledge, understanding how to apply this advanced tool to your particular research, but also enjoy KTH and Stockholm, since the weather seems to be quite good. I'm going to say a few words about where we are and the project and what are the goals of the summer school and what is the agenda. So KTH was founded in 1827. So this is the main campus. Used to be another campus in close to the industrial pole in Kista. Is now closed. We still have a couple of more campuses in other areas. Originally was actually in downtown, and then we moved here, still downtown, but not as central as before. Is the Swedish largest technical university. So if you're coming from a polytechnic school, that's probably the closest one to what you have in mind. It means that we do not cover typically literature, but we focus on engineering, architecture. And also we have a music school. That's some integrated. So because we are the most important technical university, probably not the largest, because we just focus on engineering, architecture school. And we roughly have 15,000 full-time students. When it comes to the ranking, we are 78 worldwide in the QS World University Rankings. This is the general. When it comes to the most technical, like engineering school, we are in the world placed in 2026, number 33. So is a highly ranked international school. One thing I really like about KTH is really the motto, which is Vetenskap och konst, which means science and art. So the university and technical school has in his genes the fact that engineering aspects and science aspects are tightly coupled with art and a sense of beauty. So you will see the logo here, and then the major motto that basically says science and art. We are in the organization. So myself, Yuna, belongs to one of the 5 schools that are here at the KTH. The one that is comprising both electrical engineering side, comprising also plasma physics, space, and fusion, and computer science. So he has these 2 souls. So it's one of the 5 schools. The school are, for instance, quantum chemistry, science, and we are the largest one, possibly because we are both combination of electrical engineering, including electronics, plasma, and the computer science experts, including AI. Most importantly, for this summer school, our school comprises expertise in some key area that we're going to discuss this week. One is in plasma physics, space physics is in our school. And also we cover basically all the fundamentals of AI. So from machine learning, AI, novel technique is basically having professor in our school. Our school is one of the largest, include roughly 4,500 students, 500 PhD students, and roughly 1,000 people in all the staff. So these include administration and also faculty member here. The summer school that I'm going to introduce now is supported by a large project at the European level. called ASAP, where the A stands for automatics. So that's where it comes to AI part that we're going to focus on this week. It's a European project, so it's funded by the European Commission, which has also as one of the goals to train the next generation scientists working on the area intersection of AI and space application. And therefore, that's why we're having this summer school this week. The project is specifically looking at developing AI-driven automation, so automatic techniques that can be deployed without having the humans directly involved for a future mission. So, for instance, ESA mission, and especially looking at how some of the technique can be embedded on the spaceboard, or which one should be on the spaceboard, which one should be on the ground, and how to combine a different technique. There are four main pillars. So the first one is looking at AI and machine learning techniques for analyzing space data in an automatic way. There are other three pillars, more looking at the technological development. One is taking this algorithm and develop specific processor that can map directly to the algorithms. So these are called FPGA onboard acceleration. So you have a particular device called FPGA, and then you program so that is optimized for the algorithm that we're going to discuss today. We're also working on software testbed and validation. So how we can actually design this software mapping to the algorithm and then validate. Right? So validation is quite difficult topic because we cannot validate send to the space. So we need somehow a framework that we can validate and test all the algorithm on the ground. And this is connected to the last topic of the project itself, that is to develop a digital twin for the flight simulator for the spaceboard processor, which develops AI technique, so we can test using the simulator. The major interesting for the interest topic for the school that we start today is the first pillar, so AI and machine learning algorithms for space science data. However, you will meet a different professor here during the days. We're also involved on these different parts of the project, so you're more than welcome to contact us and talk about your interest if your research is touching one of these additional topics. However, we're going to focus mainly on algorithms, AI machine learning algorithms, and we're going to give a very applied edge to the summer school. So why we decide to do this summer school, and why is it important that you are here today and this week? Well, it comes to realization that nowadays, if you're a space physicist and space scientist, you will need to handle a huge amount of data. Right. So this was also true before. So like back in my time, you still have some observation, but still you're going through, you're checking it, and then you find some events that are interested, and then you publish a paper. With the technology advancing, both in technical equipment and the instruments that have been employed on the spacecraft, but also computer science technique, how to handle data, how you distribute data. The amount of data is becoming more and more larger. So just to give you an idea, so this is if you are familiar with magnetic reconnection, maybe some of you are. You might probably heard a past mission called Cluster. This is basically 4 spacecraft working in a constellation that provide the 3D measurements in 4 different points for a different quantity. So this was devised for studying monetary collection. If you're going to look at the archive, so how the data actually you have for doing your study, you'll be quite impressed, quite shocked, how the diversity of the data it is, and somehow also how difficult it is to get in a structured way. So just for the cluster active archive, which is the one that you can download from the website, you have the beauty of 3.5 plus million files, right? So if you want to basically download the full archive with all the data, let's say that you have a agnostic approach and say, well, I just want to have all the data and then I will discover the data. You will need to deal with 3.5 millions. This contains everything. Even more scary is that you're going to have 350 dataset types, so different quantities, different errors. And in total, you will have 100 terabytes of science quality data. What do you mean science quality? So this is data that has been post-processed has been processed after the measurement. So you include information of the calibration of the spacecraft, you check if the data is corrected, and you basically provide some data that the space scientist can actually use it. So 100 terabyte is compared to other facility is probably on the average. You can go easily to, if you're doing accelerator particle science, to petabyte of data. So we are small range, but the amount of software engineering when it comes to data is still not as developed as other discipline. So one of the challenges of the data is that is a lot. I would say another big challenge is the fact that you have to handle a different kind of data. So this is the problem that the machine learning called multimodality. So you're going to have different instruments, right? The information about from the different instruments might not be correlated because they are looking at a different scale or different quantity. So the data is very heterogeneous. So when it talks about heterogeneous, we're talking about a different scale, different kind of data that might be affected by the instrument in a different way. It's also multi-scale. Some of the data might be quite high level. So if you think about information about the temperature, density, some of the instruments also provide a much more detailed view. For instance, you might have information about ion distribution function, electron distribution function, something at electron scale, look at molar distribution. So you also have an hierarchy of different models that can provide by your data set. Another major issue is the time dependent, right? So because the data is basically coming from interaction from solar wind, from sun, solar wind, and Earth magnetic dipole. Any strong phenomena coming from the sun has an impact on how the plasma condition change in time. So if you're in a certain area, you observe something that might be related to some event connected to the time. So there is also these 4 dimensions, not only space, but also the time that takes into account the fact that Earth magnetosphere is highly dynamic system. So the one motivation that we would like you to have for this week is to look at the data, right? How how much data we have, how diverse is the data, and experience it. Not just download it, but look at how to manage. Can we actually make a better data set? Can we make our own data set that is supporting our research? The second motivation is that the magnetosphere, Earth magnetosphere, is highly dynamic space, and is probably one of the best example I know of complex system. Complex system is any physical system that any small modification of initial condition can result in a big change of the macroscopic configuration of the system. Think about, for instance, if you are familiar with magnetic recollection typically occurs at scales where the electrons and the ion dynamics they differ. So it is a super localized area in space, super small. Talking about a few ion skin depths. And the effect of magnetic connection that is super localized effect is impact all the dynamics of the magnetosphere. So this is extremely complex system in the same of definition of dynamical complex system, that a small perturbation somewhere has a huge impact everything else. Complex system are highly nonlinear, and so that's a lot of a physical principle, like for instance superposition, do not hold, right? So any small perturbation can basically have the big impact. So AI methods, methods that have been seeing a lot of data, methods that include these nonlinear effects that they can model beyond the existing physical model. There might be a tendency of looking at this machine learning as a black box model where you cannot see it internally. I guess one of the most critical point of view. This week, since this introductory course on machine learning AI talks, we will take them as a black box, without spending too much time. However, this is some research they're actually doing, how we can interpret the architecture, the models that we obtain from machine learning. So machine learning AI can help in understanding a wide range of phenomena that occur in space environment. We will see, for instance, how can be used to detect solar eruptions, fluorescence, and coronal mass ejection. Tomorrow we are going to start with the magnetosphere. So we're going to Earth magnetosphere. So we are going to talk about identify different plasma regions. So region where the plasma distribution are very characteristics and the change from one part to the other one can be used for characterized waves, turbulence, and quite a lot of work has been also designed for try to identify where a magnetic connection can occur. It also a very good testbed because the amount of data that we're having from the spacecraft is quite huge, right? From in situ, from observation of the sun. So is when it comes to data is really we are in a very good position. It's not one of the fields that the experimental data is missing and you're struggling. We have a lot of data. We have other challenges, but the amount of data that we have is very wide. In this course, we are going to focus on the practical aspects, right? So we know that you're a researcher doing space physics, you're working on space physics, space weather, sun, solar physics. So we are going to look at some of the practical tools that we hope by the end of the course you will be able to take and apply to your particular research part. So this This course will try to give you practical AI tools, like a toolbox, so a number of methodologies and some algorithms that in principle you could apply to your own data or the data of your own domain. Some of the tools might be helpful, some they might not, but still there. So it's also up to you how deep you want to go in a method, or how if some methods are interesting but cannot be applied, it's still okay to just let it go. So starting tomorrow, we will start, or not today, or tomorrow, to remember exactly, but looking at the problem of the data. So one of the major issues that we will find is not the problem itself, but a simple engineering problem that you have. You have an archive somewhere on the internet, available on the internet. You can push a button and download it, and then what, right? So we are going to spend some time how to, first of all, make you aware of how to do this in a consistent way, in a structured way. Also tell you that it's okay to spend a lot of time in engineering work. So there's a tendency to jump in directly in the science part, but one of the realization that you need to have in this course is that the way that you deal with data, the way that you treat, the way that you prepare your own data set is critical for your own project. Yes, you have a huge amount of data, but the way that you treat that data is available to make your own data set that you have been created with advantages and disadvantages, then this is an important part of this summer school. So we really hope that by the end of this week, you are aware of the data set that are most important for you, and you're also aware of the challenges. So how you can go from this raw data, yes, it's post-processed, it's science data, but is not prepared for doing your own science. So we want to do that. We will teach you some basic machine learning technique from basically today. Federico will be here today. So some of the technique are meant, for instance, reducing the dimensionality of the data. It turns out that the data itself is quite redundant because you have correlation between different parts of data. So you can actually, instead of attacking the big problem that might have 14, 20 dimension, you try to use some compression technique that called dimensionality reduction. So then you remove some of this correlation between the data. But then you are dealing with some kind of abstract feature. So you will learn about how to deal with highly dimensional data set and how to compress to reduce the number of dimension. How to basically in this highly dimensional space, how to put together data that seems to belong to similar distribution. So for instance, if you're looking at a distribution in density, then you can different areas of the mesosphere might have the different distribution of the density of the plasma density. So you want some automatic technique to basically tell you these are different kind of regions where I can tell you that these distribution functions are quite different. And you want to do the trick is to do automatically, right? So you have an algorithm, you take as an input the data, and then automatically split the division in different clusters. And then we want you to learn how to build a simple machine learning models. What are the architectures? So this will be very basic, very introductory. So these are the things that you need to do. We have also teacher and professor here who work on more advanced technique. but we want to make sure that you know the fundamentals well. So then later on, also when you go back to your institution, you can apply and also learn more about more advanced techniques. We're going to use tools coming from the Python, including PyTorch, that is probably one of the de facto tools for deep learning. Scikit-learn is another module, mostly for doing some basic machine learning tasks, like PCA and clustering. And then when you want to handle data in a very professional way, you need somehow also modules that allow you to organize your data in a compact way. So therefore, Panda here. The summer school agenda is basically reflecting what I told you now. So today, some fundamentals. Tomorrow will be all devoted to magnetospheric physics. And then we're going to look at space weather. So look at the collection of the sun and magnetosphere. And Thursday, we finish up with the technical topic on machine learning for heliophysics. And on Friday morning, we are going to have a lightning talk, having some talks from some people who actually work in professional in AI for space. I just want to finish up here. In the meanwhile, I want to just thank Yuna for the great work organizing this school. And then there will be a few people you will get to know during these days. And next in time will be Federica, who I saw is waiting for us. For the logistic, will be here for all week except Tuesday afternoon, so tomorrow afternoon and Friday, that we are going to move in smaller rooms just for the afternoon for the hands-on labs. We're going to have breaks. If you have the dietary restriction, please let us know. And then we're going to be the social dinner on Tuesday. Is it Tuesday?
Yeah.
Okay. Tuesday, 9th of June. And it's going to be in this beautiful restaurant. I just want to finish up, again, welcome you all to KTH and to Stockholm. And I really wish you, to have a great and fruitful week. Thank you.